So I'm going to talk about hydrologic modeling. It's just like a basic overview. And if you're a serious modeler, you probably know all this stuff, but maybe you'll find something, maybe there's something new in it. I'd say this kind of contains everything I know. So, so we're going to talk about hydrologic processes, hydrologic modeling, and then the different hydrologic modeling approaches. So the hydrologic cycle, this is what you see in any hydrology textbook, like on the first page. And I like to show it because it's just like, it just shows the complexity of hydrology and how there's so many things involved, like the precipitation and snowfall and snowpack melt and runoff and surface runoff and streams and aquifers, and then everything kind of flows down toward the ocean. And hydrology is like a conglomeration of sciences. It's really, I guess now kind of hydrology is a science, but I guess when I started in it was really just, if you did it at a consulting firm like I did, it was just a practice. But if you wanted to like get into the science of it, people came from every possible background. And so it's not like river hydraulics where it's like one thing. It's a whole bunch of things, and there's a whole bunch of, so it's complicated, and that's the net of it. I talk about sources of stream flow. So we're usually interested in stream flow. So where does it come from? You get Pertonian infiltration, excess runoff, saturated source areas, exfiltration, and then groundwater discharge to the stream. And I'll talk a little bit about each of those. Infiltration, excess runoff is, it occurs when the rainfall intensity it exceeds the infiltration capacity of the soils. And that process was first described by Horton. And so people talk about Hortonian runoff. So if anybody says Hortonian in this class, they're talking about this process. It's a dominant runoff mechanism in arid to semi-arid regions. You can think, right where you're sitting. So, where does it happen? Where you have fine textured soils like silts and clays, get high intensity precipitation like thunderstorms, and then the water table is deep and it doesn't affect the runoff. Saturated source areas, that's when kind of like the opposite. So instead of like coming from the top down, you're filling from the bottom up. And so you kind of exceeded the capacity of the soils to hold water. The process first described by Dunn and Black in the 70s. And it's a dominant runoff mechanism in humid regions. And so you can think like England, where you have permeable soils like glacial tills, low intensity precipitation, like where it just rains nonstop all day, every day. Which is how I think of London. And then the water table stays high because you have this constant flux of water down to the water table. Exfiltration happens when the elevation of the groundwater is higher than the elevation of the land surface. And this is usually not a big thing, but it may be an important thing. It's important if you're avion, right? So, people call it a spring or a seep. It's not a dominant runoff mechanism, but it can be important. And conditions that are conducive to spring are, of course, are high water table, and they generally occur in breaks in slope, where you have a steep slope coming down to a flat slope. You can think about the groundwater surface, if you're familiar with groundwater, kind of sloping down, wants to slope down kind of with the same slope it was on, but all of a sudden it hits a different slope, and so it surfaces. The groundwater discharge to the stream happens where the groundwater table is higher than the surface of the stream. And so, people talk about base flow. And the base flow is the contribution from the groundwater. So if in a class we're talking about base flow, or that term comes up, think about that's the groundwater component of the flow. It can be a significant portion of the water balance in human areas, and especially in larger basins. And generally, as you go down the watershed, in a large watershed, like think the Mississippi River, as you get lower and lower in that watershed, you get more and more base flow, and a bigger percentage of the flow is base flow. So conditions conducive to groundwater discharge to the stream are high water table, permeable subsurface materials. The water's going to flow laterally into the stream, and then again, extended period of rainfall, kind of similar to to the conditions that you get saturated source areas. So many or most basins are mixed basins, and when you learn hydrology in school, they don't like to talk about this for whatever reason. And so you get runoff generated from a variety of methods. And so you'll see spikes in your runoff, and those can be due to Hortonian flow, or spikes in runoff might occur due to saturated source areas, especially if they're near the stream. So you can see confusing things when you start looking at the data or start trying to model it. You get long tails on the hydrograph, and that's the base flow due to the groundwater interaction. And streams gain and lose depending on where you are in the stream. So up in the upper part of the watershed, the streams might be losing, and down in the lower part of the watershed, they're gaining. And so you have the watershed can act differently in different places, especially if the different watershed is large. But even tiny ones, you'll see these kinds of things going on. Special considerations are seasonality and soil layering. So seasonal plant changes affect the interception of the rainfall. Snowfall accumulation, where you get a snowfall accumulation and then melt, it completely changes the timing of your runoff and stream flow. So it's not going to be anything like you would simulate it without having snowfall. Frozen soils greatly inhibit the infiltration, can produce enhanced runoff, and rainfall on frozen soils cause a lot of major floods, and rainfall on snowfall with frozen soils cause some of the biggest floods we ever get. In temperate zones, the seasonal plant changes result in big changes in the canopy resistance during the year, and that causes a big change in your evapotranspiration, which affects your soil moisture, which affects your infiltration, which affects your runoff. So, soil layering, I'm infatuated with soil layering. Just sad, I guess. I don't know. But it has a huge effect on infiltration, and it's ignored a lot in hydrologic modeling. And so the infiltration capacity, the hydraulic conductivity, all these kind of properties, they tend to be substantially lower and deeper. As you get deeper, the soils get tighter in general. There's a special thing called a fragipan, and you see it in agricultural areas, and it's like right below where you till the soil. So a plow, I was a farmer, I grew up as a farmer. And so a plow goes about 18 inches deep, and then you're mixing all that soil up, and then when it rains, it'll leach out all the fines, and they accumulate on that area right below that, where that plow gets down to the ground, or that disc gets down to the ground, and then it gets like an almost completely impermeable layer. And so that layer can act like, even though you're in an area where you should get like infiltration, excess runoff, or tiny runoff, it might actually fill up that loosely. It might actually act the opposite, like a saturated source area. So once it hits that fragipan, it starts to fill up and runs off. So I've seen, these are just things I've kind of learned over just modeling all kinds of things. You see things like that in the beginning, and you're like, what in the world is this watershed doing to me? My model doesn't work. And so you can get this interesting thing, which is another thing that people said couldn't happen, in that the dominant runoff process can change. It can be, if you think about it, you can get Hortonian in the summer season when you get the thunderstorms and stuff, but when you get the kind of winter rainfall where it's long and you get long periods of just drizzly type weather, you can get saturation excess runoff. So that you have a switch in the dominant runoff process. Topic 2, hydrologic modeling. So numerical models, they represent the complex natural system with mathematical and empirical relationships. And so you can either reduce the complexity, or you can solve processes separately and then put them back together. And why you want to do numerical models with hydrology is they provide a mechanism for analyzing, alternatives, project alternatives, effects of future land use changes, urban development, climate change, or anything that you kind of want to play out into the future. And a key concept in hydrologic modeling or any kind of numerical modeling is the computational element. And it's important to grasp it, I think, to help you kind of really understand what you're doing. And so it's a defined region of the model where the calculations are performed. And it could be any, depending on the kind of model that we're using, it could be a sub-watershed, it could be a grid cell, it could be a control volume, it could be a finite element node. It doesn't really matter. That's your computational element. And so when you're inside that computational element, the physical conditions and the parameter values are homogeneous throughout that computational element. And that's very important because any heterogeneity within that computational element is lost. So to simulate any heterogeneity within that computational element, since you're not doing it explicitly, you have to do it implicitly, which means it ends up in your parameter values. So hydrologic modeling approaches. There's two basic approaches. There's empirically based lump parameter models, there's physics-based distributed parameter models, and then there's what people call hybrid models or semi-distributed models or quasi-physically based, where they're mostly empirically based, but they use parts of physics-based models. And so they're somewhere in between, basically. But the two basic kind of modeling categories, there's theories that these are based on, and so they have a sound scientific theory. So if you're using empirically based lump parameter models, your theory is that if you integrate over enough time and space, that all those highly nonlinear responses of the watershed, they will become linear. And then the physics-based distributed parameter model approach is the exact opposite. It's saying you break it down into small enough time and space increments, and you can solve each of the physical processes separately, and then you can put them back together and get the watershed response. So some of the kind of characteristics of the different approaches. In the empirical lump approach, you have the computational element is your sub-watershed. So your sub-watersheds, when you you got your big watershed and you chop it up into 5 sub-watersheds or 1,000, each one of those that's your computational element. That's where you're going to do your work. You subdivide watersheds into the smaller sub-watersheds. So you put a single parameter value represents the processes in that entire sub-watershed. Empirical relationships are usually used to relate the system response to the hydrologic input, and then the subbasins are connected with some type of simplified flow relationship. This is like a link node type approach. In the process or physics-based approach, our computational element is going to be the grid cell or node or finite element, finite node or control volume for doing finite volume approach. So we subdivide our watershed into these cells or nodes, and then the parameter values can vary in each cell or node. The point physical processes like infiltration, ET, et cetera, they're computed at the cell and node level, and then the cell node level responses are integrated to get the watershed response. So some advantages and disadvantages of the different approaches. So empirical models, simple to understand and use. There's a long history of use. I mean, going back to the 70s, a lot of these models that we still use today are really old. And with that comes regulatory acceptance because you kind of understand the model, you've seen it, it might even be written in a lot of places, they're written into the codes. And so that's an advantage. And then short simulation times facilitate automated calibration methods. And that's an important factor because we know that in calibration, there's a lot of different parameter sets that can produce the best result. And if you have short simulation times, you can really explore that parameter space. And you can recalibrate if you get more data really quickly. And so that's a big advantage there. The disadvantage is you tend up lumping a lot of information. If you lump it into the subwatersheds, they're probably quite large compared to a computational cell in a physics-based models. There's usually no process information provided. It doesn't help us understand the watershed. We're just modeling the response, and we're not really trying to understand the watershed. The parameters have limited physical meaning and may be difficult to estimate when you're changing conditions. So if the conditions change and your parameters are tuned basically to the data, you may not know how to change that parameter. I ran into that many, many years ago, and that's what kind of got me interested in physics-based modeling. They're not reliable outside the range of calibration, which can lead to a I can't say that, verification problem. I can't say that word today. Somebody say it for me. So switch over to the process-based models. So, I mean, it's just a flip. It's almost like a complete flip. So they're more difficult to use compared to, I mean, it's not a new technology. You got to remember, thinking about this, I've been doing this since the 90s. So, in 1995 was an extremely new technology, but now it's still relatively new. You may still need to justify the use to regulatory agencies. That really hasn't changed. Long simulation times can hamper calibration efforts. I mean, if your simulation takes 2 days, I mean, how many parameters sets can you analyze, right? The good thing about it is you explicitly include spatial heterogeneity. You have kind of the luxury of defining that resolution. You don't have to, like doing sub watersheds, you have to put some effort into picking the sub watershed. But if I want a 100-meter grid or 50-meter grid, I just use WMS to make me a new grid, and I have a new grid. The model helps the user understand the physical process. So a lot of times we use GSSHA and other models like it are used to, it's like, what is exactly the controlling processes in this basin, or how does this fundamental process, if we change this fundamental process, how will that change the system response? The parameters have a physical meaning and they don't change with changing conditions, which is nice. If you want to change things, you want to rearrange the land uses and stuff, once you have those parameters nailed down, the sand response isn't going to change as you move it around the watershed. That lets us use the model for new conditions, which is a really nice strength of this approach. Hybrid models, they have elements of both, and the approaches vary amongst all the different models. There's a lot of them out there, and some are very empirical and some are very physics-based. So it's just kind of up to the guy that developed the model and what he thinks is important. They share many of the same advantages and disadvantages as the lump parameter models. They typically include greater spatial variability than the lump parameter models do, and they may include some physical meaning representations of the processes. They may include some physical processes in their models instead of just empirical representations. And in general, they maintain the computational advantage over the fully distributed physics-based models. They're not going to add enough stuff to make it a beast, I guess. That's what I would say. So, you got all these different tools, and you're an engineer or a scientist, and you want to make use of them. And so it's kind of like, what? And I get these kind of calls all the time where it's like, I'm thinking about using this model for this project. And so is it a good fit to the project? And so if you can think about it, just kind of loose, broad terms, empirical models are best for analysis of current systems. I mean, if you think about the advantages and disadvantages, that's kind of obvious. And so the nice thing about it, it can be applied to very large basins. Say I want to model the Mississippi River or the Amazon River basin, thousands and thousands of square miles. I can do it with that type of approach. And I can do it pretty easily, actually. And they can provide predictions within the range of calibration. So if I have a nice data set and I calibrate my model, and I can be pretty comfortable, doing analysis within that range. And it can identify areas of concern. So I find in areas like, there's something there's something going on here. I need to dig in and get more physics based. I can always go in with a finer model and analyze that area. So the National Weather Service, we're sitting in the National Weather Center. The River Forecast Centers, they use the Sacramento model for flood prediction. Sacramento models was written back in the 70s. It's extremely old model. It's very simple. It's like a volumetric model. Put water in different buckets and put it back together. It has these different zones, and these centers, there's constantly data coming in, so the model is constantly being recalibrated. So you think about it, if you're constantly recalibrating, you're constantly extending your calibration, and you're accounting for changes to the system because it's just going to change over time. And these models work very well, and you will have a very hard time beating a forecast from the River Forecast Center with any approach. So that's a great example. I like this example for like the distributed modeling approach. Like, you just said, well, you can use a simple model and do great. Well, you can, but it's not the best for everything. This Goodwin Creek experimental watershed, Goodwin Creek is where we've kind of tested everything we've ever done. And so, and a lot of other people have too. So if you look at it, it's nice because it has a tremendous data set. And so if you look at this thing, the red and orange areas are areas where there's sediment erosion, and green areas where there's sediment deposition. So only erosional areas near the stream contribute to the sediment load. And so, the path matters. So if you were just to look at the percentages of erodible area and try to simulate the sediment in the stream, you would fail, because those areas, I don't know if you can see this pointer, but like areas up here, this eroded, it's going to get caught in these green areas. It's never going to make it to the stream, whereas these are going to get into the stream. They're just going to get dumped right in there. So in this case, we really need to pinpoint the areas, and we need to pinpoint the path, because sediment deposits along a path. So your modeling philosophy, or my modeling philosophy, which it's my class, or it's Aaron's class today, but it's my recitation. So it's yours. Yours for today. Models should account for the dominant physical processes. I'm a process guy. I really believe that we need to include our processes to do a good job of modeling. So the model has to include the physical features, both temporal and spatial, as they change over time and space. The model should not have undue complexity. A lot of people, when they've been doing an empirical type approach, and then they see the physics-based approach, and they want to model an enormous basin at 10 meters so they can catch every rooftop, and that's not helpful. A big thing is that the model approaches are different for different problems. So I guess it's not the best model for everything, or any other model for that matter. So you should use different models for different problems. And the model representation of the physical system should be as simple as possible, but no simpler. Yeah, question. It's in Mississippi, North Mississippi. There's probably at least 100 scientific papers published on Goodwin Creek. Wouldn't you say, Billy?
PhD. So.
Yeah, so many. It's just it's a nice place to test any model, and it's got a really nice data set for all kinds of things, like soil moisture. No, it's kind of rolling hills.
It's right outside of Oxford, Mississippi.
And it's so big rain gauge network, scan weather stations, the soil, sediments, water temperature, water flow.
So it goes back to the 1980s when they started collecting information there. So this is like an 8.3 square mile watershed, and they have maybe 15 flow gauges on that thing.
At least, yeah.
And then maybe 20 or 30 rain gauges on that thing. So, I mean, obviously you would, I mean, it has to be a research watershed to have that kind of data set.
Yeah.
But it's an excellent, watershed for, when you're developing new algorithms and you want to really see what, if it's really reproducible. I mean, it's just a great data set.
Yeah, we've done all kinds of stuff and other people as well. Like you can really like that, like having all these nested gauges, you can tell, if your model is really matching, can you match all those gauges, right? Or just, can you just match the outlet, right? So, and other things like that. And then the sediment, a lot of sediment models have been tested there, including ours. So it's a really nice.
Yeah, so the sediment lab, which is in Oxford ARS, that the primary purpose of using reading is to flow the stuff. And then over time, they've added things like nutrients, water, temperature as funding, became available so they could go out there and collect. So if you look at the data set, you'll see a pretty good flow in sediment, rainfall and all that. And you'll see periods of time when they did a good job on water temperature or nutrients or whatever, but it's not for like 40 years. So it's just whenever they had funding to support, that kind of.
Okay, so for all the Python programmers, this is what you can try to remember. This one. So hydrologic cycles complex, hydrologic models, they aid in our understanding and analysis of the systems. And there's two big classes of models, empirical parameter models, distributed physics-based models, and then hybrid models that contain elements of both. We use these different types of models for different purposes. Models are best for analysis, physics-based models are best suited for design, and then hybrid models kind of task in between, refine analysis, screen design. Then our physics-based models, I didn't really get into this, but the range of complexity actually varies tremendously if you look across some of them. And then the appropriate model just depends on your application. I think that's my last slide. How we doing? We catching up? I usually talk pretty fast. Are there any questions about any of that stuff before we